Hey everyone, it's time to come back to the functional groups that we learned at the very beginning of this chapter, and we're going to learn how to name these different functional groups. And then after we've done that, we're going to go and talk about some general trends in physical properties such as melting points, boiling points, and solubility. So when we name organic molecules, we're going to expand on what we've been doing naming alkanes, branched alkanes, and cycloalkanes. So let's kind of generalize our naming system. Okay, here in the middle in red is the parent hydrocarbon. So this is the parent name, typically the longest carbon chain. We'll see in some cases it's going to be the longest carbon chain that holds or bears the highest priority functional group. All right, so the functional group can either be named as a suffix, okay, and we've already seen situations like this where the suffix might be ane for an alkane. We've just seen a few examples of these, but ene for an alkene, which has a double bond, or yne for an alkyne, which has a triple bond. All right, so we've seen some examples of functional group suffixes. We're going to see two other types of functional groups in this section that we name as suffixes, and those are going to be the alcohols and the amines. Okay, another way that groups can be named is as a functional group prefix. Usually we use this functional group prefix when we are naming molecules with multiple functional groups. And in those cases, we have to prioritize one functional group over another. The highest priority functional group gets to be the suffix, forcing the weaker functional group to be the prefix. All right? So we're not going to really do something as complicated as that so far, but we are going to do like we've done before, and we're going to list our substituents out in front. So these substituents can be things like alkyl groups, right? We've done this already. But other groups that we can name in this way are ethers, okay, which usually has some alkyl group attached to an oxygen. So this is going to be attached to our parent. And the other group that we can do as a substituent are halogens. And these halogens typically, as we've talked about before, the ones that we will look at can just be named as a fluoro, chloro, bromo, and iodo. All right, so let's see some examples. The first group of molecules that we're going to name are the alkyl halides, or the haloalkanes. So what we do in these cases is we name them just like the halogen was a methyl group or an ethyl group. We just treat them as another substituent. There's no priority at all. So if we start on the left, we're just going to pick out the longest chain that bears, or just the longest carbon chain, right? So that's going to go down like this. We're going to number that chain to give the substituent. In this case, we have a chloro. Give it the lowest number. So we're going to number it this way: 3, 4, 5, 6. So this is just 3 chlorohexane. All right, simple. The next one has a few more substituents, but again, we're going to pick out the longest chain. And we're going to name all of these different groups as substituents. Right? We're going to number this to give the first substituent the lowest number. So we number it from left to right because that puts the first substituent at the 2 position. If we numbered it from right to left, 1, 2, 3, the bromine would be at position 3, but we want the first group. Bromine has no priority, so we just want the first group, the lowest number. So we can get it at position 2 if we number this way. So this is 3, 4, 5, 6, 7. So this is a heptane, right? We're going to list the groups in the substituents in alphabetical order, though. So this is going to start out as 5-bromo. And then we have methyl groups at 2 and 4. So 2, 4, dimethyl heptane. All right, just one more example. We're going to number this to give the second group the lowest number, but of course in this case there would be a tie, right? We could number it from this side 1, 2, 3 going clockwise, or we can number it from the iodine 1, 2, 3 going this way, and we'll break that tie by giving the ethyl group the lower number because ethyl comes before iodo in the alphabet. Okay, so we'll just do it this way. We will have 1 ethyl, 3 iodo, cyclohexane. All right, so straightforward. We just treat the halogens like they were just another alkyl group. Okay, well, what about the ethers? So the ethers we're going to treat as a substituent as well, but let's just, on this first one, I'll show you what is oftentimes done as a common name. And remember, I won't test you on this, but just you'll probably hear it sometime. So for this is a really common ether, and so essentially the common name looks at the two alkyl groups attached to the oxygen. Okay, and so, and then just say ether. So this one is diethyl ether, separate words. Okay, so that's the common name for this. But for IUPAC, what we do is we are going to choose the longest alkyl chain. So for example, in diethyl ether, we have two ethyl groups, so we can pick one or the other as the longest chain. So let's just say we're going to pick this as the longest chain. So this would be named as an ethane. Now, the rest of this is going to be named as a substituent. Right? A substituent, remember, is something that's attached to the parent. So what we do here is we look at the alkyl group. So this is ethyl, right? But there's an oxygen on it. So we're going to cross out this YL, and we're going to add oxy. So eth-oxy. Okay, if we look at this in general or generic terms, we have an alkyl group, and we change that to alkoxy. So it could be a methoxy, ethoxy, butoxy, something like that. All right, so this one is going to be an ethoxy. And since ethane only has 2 carbons, the ethoxy has to be at position 1 because we're going to number it that way. So this is just ethoxyethane. That should be all one word. All right, so let's look at the next one. So we're going to pick the longest chain. All right, so on the left side we have 1, 2, 3, 4 butane. On the right side we only have 3, so that's a propane. So our longest chain is going to be here. All right, so we are going to have a butane, and this group right here is going to be the substituent. So we're going to go 3 carbon piece propyl, and we're going to cross that part off and make it propoxy. Alright, so we're going to number this 1, 2, 3, 4. Right, so this is going to be 2 propoxy butane. Alright, so let's just do one more. Here's a cycloalkane. Right, so this is a cyclopentane, right? We can look at our 2 substituents. We have a methyl. We actually have 3, methyl and methyl. And then what's this one? This comes from methyl, but so this is methoxy. Okay, so where are we going to start numbering this? Right, we're going to start numbering it where we're at one of the substituents as number 1, and we want to number it so the second substituent gets the lowest possible number. So we're going to number it here, 1, 2, 3. So the second substituent is also at position 1. Okay, so this is going to be a cyclopentane. That's the parent, right? And these are methyls, dimethyl, but remember that di doesn't get alphabetized. So which one comes first, methyl or methoxy? So methoxy should go first, because when we go to meth, this one has a Y, and there it has an O. Just like looking up a name in the phone book if you've ever done that. Alright, so we're going to do the methyls first. So this is going to be 1,1 dimethyl. Dang, I'm not going to fit this in though. 3 methoxy cyclopentane. Alright. Next functional group are the alcohols. Okay, so alcohols we're going to name, remember, as a suffix. So it's the OL that's going to tell us. So we could start with an alkane name, and if it has an alcohol on it, we're going to drop the E, and we're going to add OL. Alkanol. Alright, so this is going to tell us there's an alcohol. So if we go to the simplest one, here this would be for methane, right, would be the alkane, so this is just methanol. Okay, for common, sometimes you'll see common names will be things like methyl alcohol. Alright, so that's a common, but we're going to do the IUPAC, which is in blue. Okay, so here's a 2 carbon piece, so ethane, ethanol. Alright, so that's the alcohol that's in, alcoholic drinks. Methane is sometimes called wood alcohol. So the next one, propane, and we number this 1, 2, 3, either way, right? So this is 2 propanol. So the 2 is telling where the alcohol is attached. Alright, the next one, we've got the alcohol and we have the methyl group. Look, if we number this 1, 2, 3, 4, 5, the first group is the methyl group at 2, or if we number it the other way, we have the alcohol at 2. So in this case, with alcohols, the alcohol takes priority. So we always number this chain so the alcohol gets the lowest number. Okay, so this comes from pentane and 5-pentanol. So we have 4-methyl 2-pentanol. Alright, so look at this next one. So this one's kind of confusing, so let's look. What's the longest chain? The longest chain would go all the way along here, right? But that would leave the alcohol off. So the alcohol is the highest priority. So we have to number the longest chain that includes the alcohol. All right, so our numbering is going to go this way. And remember, we're going to number this to give the alcohol the lowest number. 2, 3, 4, 5, 6, 7. All right, so what do we have? What substituents do we have? We have a propyl over here. And what else? We have this group. What's this? This is a methoxy. All right, and that's all going to be on a heptane, and we have an alcohol, so a heptanol. So we have 2 heptanol, right? And then we have methoxy and propyl. Methoxy comes first, so 6 methoxy, 3 propyl, 2 heptanol. All right, so the next one has 2 alcohols, right? So it has, we can number this 1, 2, and so this is called a diol. So there's 2 alcohols. So this one we can either call it 1, 2 ethane. We leave the E when we have diol or triol, ethane diol. One thing that we could do in each of these cases, in fact, another place that we can put the numbering is right before the ol or the diol. 1, 2 diol. In fact, we could do that up here. We could call this propane 2-ol. Okay? Alright, so 1,2-ethane diol is also a compound that's called ethylene glycol. Okay, this is a common name. Maybe you've heard of that before. Alright, so our last one, 1, 2, 3, has 3 alcohols. So this is actually a triol. So we could call this propane, right? So 1, 2, 3, propane triol. Or it could be propane 1, 2, 3 triol. Okay, this has another common name. We've heard of this one is glycerol. Glycerol is really important in biochemistry and biology, because if we connect a fatty acid to these 3 alcohols to make a functional group called an ester, then we have a triacyl glycerol, which is a common type of fat. Alright, so one other important aspect about alcohols is that we can have a classification system like we did for carbons. Remember, primary, secondary, tertiary. So for alcohols, what we do is we look at a given alcohol, like this, or like ethanol, and we count the number of carbons attached to the carbon that's bearing the alcohol. Alright, so in this case we look at that carbon right here. It's only attached to one other carbon, so we call this primary alcohol. This one has two carbons attached, so this is a secondary alcohol, like this one, a secondary, right? If we have a tertiary alcohol, we could have something like this, right? So we could have 3 different methyl groups, for example. This would be tertiary. All right, we could call this one tert butanol. Or we could number it across like this, 1, 2, 3, and we could call it 2-methyl 2-propanol. All right. So primary, secondary, tertiary. All right. We'll see that in some cases, having the different substitutions of the alcohols will impact their reactivities. All right. So the next group are the amines. Now, amines are nitrogen, and they can have hydrogens attached, or they can have alkyl groups attached. All right, so in naming amines, we take the longest chain that bears the amine, so the alkane, the parent, and we drop the E just like we did in the last one. It was pretty easy. We just add amine, alkane, amine. All right, so the simplest of the amines we've run into before, right? So that actually has all hydrogens attached. So this is just ammonia. And remember, for nitrogen, it's neutral when it has 3 bonds, and the other thing that's not shown is that it will always have a non-bonding pair of electrons. So amines, one of their primary roles that they play are as bases reacting with a proton. Okay, so our next one, we can just start numbering 1, 2, 3. So we'd have to name this 1-propane amine, right? Versus we have to put the 1 out in front because that amine could be at the 2 position. All right, the next one, find the longest carbon chain that has the nitrogen attached. Right, we're going to number that chain to give the nitrogen, the amine, the lowest possible number. So we'll number it from this side. All right, so it's hexane amine. Right, and the amine is at the 3 position. Now the substituents that we have in this one is we have a methyl right here, and we have an ethyl over here. Right, but how? Look at one of them, the methyl group, is attached to the parent at the 5 position, but the ethyl group's actually attached to the nitrogen. So how do we tell that that ethyl's on the nitrogen and not on the parent? Okay, so what we're going to do is if an alkyl group or a substituent is attached to the nitrogen, we'll just put an N out in front. Okay, so ethyl comes first in the alphabet, so we're going to say N-ethyl, 5-methyl, 3, there'd be a hyphen in there, 3-hexane amine. All right, so here's a common one. This has a common name. We use this a lot in the lab. It's just usually referred to as triethylamine. All right, but that's not how we would name it from the IUPAC, right? We'd pick the longest chain, so there's only ethyl groups, so we'd have to pick one of those. So this would be for an ethane. Oops, let me make some more room there. This would be for an ethaneamine. right? And then we have two other ethyl groups here and here, and both of those are attached to the nitrogen. So this would be N diethyl ethanamine. So triethylamine is kind of easier than that, right? Okay, so here's just a kind of a couple of common diamines. And a lot of these amines have an odor, so you've probably smelled ammonia, right? It's in Windex glass cleaner and things like that. So these diamines have some really strong odors. And just to give you a little hint about that, here we have two different ones. So we can have diamines with the amines on the end. So I did these a little bit wrong. So if we have this as having 4 carbons in the middle, so there's 1 on each end, so N would be 2, right? So we would have 1, 2, 3, because there's 2 of them in here, 4. So we have 4 amines, 4 carbons, I mean. Sorry, I'm getting distracted. And this molecule has a common name, and it is called putrescine. That sounds nice, huh? Tells you something about how it smells. So, and then if this is 3, so we have 5 carbons between the amines, this one is called cadaverine. That smells nice. That sounds nice. All right. So these would be called, right, if there was 4 in the middle, it would be a butane diamine, 1,4-butane diamine, or 5, 1,5-pentane diamine. So amines can also be classified like we did the alcohols and the alkanes based upon a terminology of primary, secondary, and tertiary, but amines are classified differently. All right? So for amines, what we do is we look at the nitrogen and we look at how many carbons are attached directly to the nitrogen. So this nitrogen has 1 carbon attached, so this would be primary. This carbon has 2 alkyl groups attached, so this is secondary. This nitrogen has 3 carbons attached, it would be tertiary. And we also have a possibility of nitrogen having 4 groups attached. Something like this, which would put a plus charge on the nitrogen, and this, which is an ammonium ion, would be quaternary. This would be a quaternary ammonium ion. So here's a summary of the naming that we've just done. I'm not going to read through it all. I think you guys can take a minute and read this, but we ought to be able to recognize, come up with names for different molecules. We ought to be able to see a name and write out the structure. All right, so we're going to talk some about the physical properties of organic molecules. Particularly, we're going to look at these 3 here, the boiling points, melting points, and solubility. So whether it's, like we talked about before, whether it's water soluble or organic soluble. And each of these different physical properties involves intermolecular interactions. Right, or intermolecular attractions. Okay, because if we have a a boiling point. We're going to have a liquid, and when it boils, some of that compound is going to break out of the condensed phase, out of the liquid, and escape into the gas phase. So there are forces that are holding those molecules together in the liquid phase, and it has to have enough energy to break those attractions to escape. So the three types of interactions or attractions that we're going to look at here are, the first one is called van der Waals attraction. Okay, Gen Chem, this might have been called dispersive forces. The second one is dipole interactions. And the third one is really another example of dipole interactions, but we're going to list this separately. This is hydrogen bonds. Okay, so let's look at a few attractions. So van der Waals attractions are kind of an interesting thing. So if we look at it really plays the biggest role in things like alkanes, or when we have very non-polar molecules, a lot of carbons and hydrocarbon portions. And when we have non-polar molecules, there's no polarity, there's no plus and minus attracting each other, which tend to be the stronger interactions. So for van der Waals interactions, what we essentially have is molecules, when they bump into each other, they kind of push the electrons around, and we have a transient interaction. So this is very short-lived. We push the electrons around, and so we generate a partial plus on one part, and that bumps into another. It attracts the electrons to it, and we get a delta minus here, but those electrons went here, we have delta plus. And so these are what we call induced dipole interactions. So the dipoles are induced by kind of being pushed around in a very transient type of situation. So let's just look at what the boiling points are of these different molecules. So here we got a series of molecules, increasing number of carbons. So if we look at methane, its boiling point, these are all going to be in degrees Celsius. So the boiling point is minus 167.7 degrees. So it's very low, right? So it's always a gas. Ethane, minus 88.6. Propane, minus 42.1. Butane, minus 0.5. Pentane, 36.1. And hexane, 68.1. Right? So we can see that if we have increasing mass, we have increasing boiling point, right? So the boiling point is increasing. All right? And we might notice that there's an important cutoff here, which is right here. Right? So this is an important cutoff where on this side at room temperature, these would be liquids, and down below it, these would be gases. Okay? So it's not really the mass that's important, it's the amount of surface area. Okay, so as we go this way, we have greater surface area, because it's the surfaces that are going to bump into each other and create these transient dipoles. All right, so what do you think? If we look at the boiling point of methane, is that low? Is it high? Is it surprisingly low? So let's compare it to another molecule of about the same mass that we all know, right? So what if we compare that to water, right? Water and methane. Methane has a mass of 16, and water has a mass of 18, so they're both very similar. But what's the boiling point of water? Right? The boiling point of water was 100 degrees Celsius. Look at the difference between these two. We should put a couple exclamation marks here. Look at how high the boiling point of water is for such a small molecule. What does that mean? So for water to have such a high boiling point, it means that it must have very strong intermolecular attractions. Very strong All right? So we'll talk about those interactions in just a minute, but just think about it. What if water had its boiling point down at minus 167.7? Right? So that means that every temperature above that, water would be in the gas phase. Right? So all the water in our bodies would just evaporate. Right? The ocean would evaporate. The lakes and streams would evaporate. There would be no liquid water on the planet, meaning that we could not have life like we have it. So just a very simple concept like this has great implications. All right, so let's look at another example of how surface area makes a difference. All right, so look at these three molecules. We have pentane, right? So it's just a 5-carbon chain. We have 2-methylbutane, so it still has the same molecular formula. What's the relationship between these two? Right? So they have the same formula, but they have a different connectivity. These are conformational. No, they're not conformational isomers. They are constitutional isomers, right? Constitutional. We talked about conformers earlier. Isomers. Right? And here's another one. Look at that 2,2-dimethylpropane. That's another constitutional isomer. All right? So they all have the same number of carbons. They all have the same number of hydrogens. So they have the same mass. But look at the difference in their boiling points. For pentane at 36.1. For 2-methylbutane, 27.9. For 2,2-dimethylpropane, down to 9.5. Right? So as we have more branching, so this is more branched, right? The boiling point goes down. All right? So why would that be? Right? So the reason is that pentane has lots of surface area. Okay? Whereas 2,2-methyl-dimethylpropane is more like a ball. So it doesn't have as much surface area to stick together, right? It's like a ball. It has little surface area. Right? So less surface area means that there's less van der Waals attractions, and so the weaker attraction means that it takes less energy to evaporate the sample. Right? So the boiling point is lower. All right, so let's look at the next type of attraction. Dipole-dipole interactions involve molecules that have a permanent dipole. So they have two atoms or atoms of a bond that have different electronegativity. So let's just start out with some generic case. Maybe we have some two molecules, X and Y, and X and Z, and let's say that Z is more electronegative than X. So Z will have a delta minus on it, leaving X with a delta plus. So we have this polarity in one molecule, and that's going to orient itself to another molecule, but in the opposite direction. So there's going to be an attraction between the delta minus end, the Z, and the X end of another molecule. So delta plus, delta minus, and these are going to continue on like this. Okay, so this is always partial pluses and partial minuses being attracted to one another. All right, and this is going to include all of those atoms except for hydrogen. Hydrogen is a special case, and we're going to look at that on the next slide. All right, so examples of this could include things like this. This is a molecule called acetone. Okay, it's a common organic solvent. It's in fingernail polish removal, and it has this carbon-oxygen double bond, which is called a carbonyl group. And you're not going to really learn too much about these until next semester. But this carbon-oxygen bond is polar, right? So oxygen is more electronegative than carbon. So we have a delta minus on the oxygen and a delta plus on the carbon. In addition, this oxygen has two pairs of non-bonding electrons. This is partially where this delta minus lies. And so acetone one molecule of acetone will be attracted to another molecule of acetone through its non-bonding electrons. And so this molecule of acetone will be attracted to the delta plus side of another acetone molecule. Likewise, this acetone with delta minus will be attracted to this carbonyl end, the carbonyl carbon end. And so we have these dipolar attractions like this. All right, another example could be with something like an ether. Right, so the oxygen is more electronegative, so we have a delta minus here, leaving delta pluses on the two carbons adjacent to it. And so this oxygen can be attracted to the delta plus side of another ether molecule, like this. Okay? Now, these types of dipolar attractions are especially prevalent when we have kind of small molecules. If we have one functional group and then just a lot of hydrocarbon, then the van der Waals attractions become more dominant. All right, so let's look at kind of a trend of some small molecules here. Okay, so we're going to compare alkanes and ethers. Okay, so we're going to start with propane. Okay, and we're going to put the boiling points over here, and these are going to be in degrees Celsius. All right, so propane has a boiling point of minus 42 degrees. Okay, so it's very low. Propane, as you know, we go fill your propane tank, and I use one on my barbecue. Okay, so let's compare that to an ether. So methoxymethane or dimethyl ether. All right, so we have some polar bonds here. The boiling point of dimethyl ether is minus 24. All right, so notice that the boiling point is still very low, but it's gone up from the alkane. Right, so there's stronger intermolecular forces. Okay, let's go up to the next size. Butane has a boiling point of minus 0.5. All right, and if we look at methoxyethane, so we have a methyl on one side. We still both have the same size, right? There's only 2 mass units apart. the boiling point goes up to 7.4. So again, we have these polar bonds creating this dipole-dipole interaction, slightly stronger than what we're seeing for the pure van der Waals interactions. However, when we get up to pentane, okay, the boiling point of pentane is 36.1, right? So this is that's above room temperature, so this is the first of the alkanes that is liquid at room temperature. And if we look at diethyl ether, okay, this is also a common laboratory solvent, so it's also a liquid at room temperature, and the boiling point is actually 34.6. So it's, they're almost the same. And so once we get up to this size and bigger, the van der Waals interactions become more important. All right, so let's look back over here at acetone. So acetone was over here, right? And let's compare it to one of those molecules of the same size. So we have 1, 2, 3, 4. We have 4 kind of heavy atoms, right? So that's right in this range right here, okay? Excuse me. All right, so the boiling point of acetone is actually 56 degrees Celsius, right? So notice how much higher the boiling point of acetone is to either butane or methoxyethane. So that tells us that the intermolecular attractions, or the dipole-dipole attractions, is much stronger with this carbonyl group than it is for either the alkane or for the ether. All right, so the last type of intermolecular attraction that we're going to look at is the hydrogen bond, and this is really just another example of a dipole-dipole, but it's kind of a big group in its own right, and it's very important in biology and biochemistry. So let's imagine now we have a bond, and in this case the hydrogen is going to be more delta plus, so it's going to be less electronegative than whatever this Z group is, all right, and delta minus. So most commonly, the types of bonds we're going to be looking at are oxygen-hydrogen bonds, right, which we know have a delta plus on the hydrogen and a delta minus on the oxygen, and nitrogen-hydrogen bonds, right? So again, nitrogen is more electronegative than hydrogen, and so we have this type of polarity, okay? So one example of a molecule that has a lot of hydrogen bonds, that has a great effect over its boiling point, is just water. So water, remember, has a bent structure like this because the oxygen is sp3 hybridized, right? It has 2 non-bonding pairs, and the 4 pairs of electrons around the oxygen are in a tetrahedral. Right, so this has the delta minus on the oxygen, delta pluses on both hydrogens. Okay, so this oxygen is attracted to a hydrogen of another molecule. All right, this hydrogen down here might be attracted to an oxygen of a water molecule. Right, this one up here might be attracted to another one. This could be attracted to an oxygen. And so as you see, we create a big network of hydrogen bonds. All right, and it's this network of hydrogen bonds that makes the boiling point so high for water for its size. All right, so the strength of the hydrogen bond depends upon the polarity of the bond. So the more polar the bond, the stronger the hydrogen bond. All right, so more polar. We get a stronger hydrogen bond. So which do you think would give a stronger hydrogen bond, the OH or the NH? Right, so the OH would give a stronger bond, right, because it has a greater difference in electronegativity. Oxygen's more electronegative than nitrogen, and so OHs are generally stronger hydrogen bonds. Okay, we can see the same thing as that we see in water in alcohols, right? So here's an alcohol. Notice that the difference here between the alcohol and the water is just that we've traded in one of the H's for an alkyl group. Remember, this R is alkyl, or generic organic, right? So this could be attracted to the oxygen of another alcohol. This could also be attracted to the H of an alcohol, right? And so we can also have this network of hydrogen bonds, but notice that alcohols only have one hydrogen bond that they can make instead of two. And so an alcohol is going to have a lower boiling point than, well, we can't really compare it to water. We can't have one that's the same mass, but alcohols still have quite strong boiling point. So the boiling point of an alcohol will be much higher than the boiling point of an ether for the same molecular mass. So let's look at some NH hydrogen bonds. Let's just look at a series here of amines. Okay, so here's propane amine. Here is N-methyl ethanamine, and we'll just call this trimethylamine. All right, so which of these, so again, let's just remind ourselves this is a primary amine, this is a secondary, this is a tertiary. All right, so which of these do you think would have the highest boiling point? So which would have the highest intermolecular attractions? All right, well, let's look at the boiling points. Okay, so the boiling points of these are 48. Okay, these are all in degrees Celsius. 48. What about the secondary? 36 and 2.9. So look at it's going down. So I think that there's two things that we can look at here. The first one is going to be the most important. The first one is that for the primary amine, it can have two hydrogen bonds, right? Because it has two NH bonds that can both hydrogen bond. The secondary only has one hydrogen bond. And what about the tertiary? The tertiary has no hydrogen bonds. All right, so it's relying only on dipole-dipole interactions, not hydrogen bonds. The second thing that we might look at here is that, remember when we look at van der Waals interactions, the more linear the molecules, the more surface area that we can have van der Waals interactions. And so this primary amine on the left, right, has a much more linear structure, so there would also be van der Waals interactions here, and as we go to secondary and tertiary, this is starting to look much more like a ball, and so not only do we not have hydrogen bonds here, but the van der Waals interactions would be quite weak as well. Okay, so here's just a couple of more examples. All right, so one trend we know is that if we add an extra carbon, right, we go from propane to butane, we're going to increase the boiling point, right? We have more surface area, more van der Waals interactions. And this happens in each one of these examples, right? So for an alkane, an ether, alcohol, amine, if we add another carbon, then the boiling point goes up. because we're increasing the van der Waals interactions. Okay? Then, if we look across these functional groups, we see that when we have small molecules, at least, we can go from alkanes to ethers, and we're going to see an increase in boiling point. Remember, if we get much bigger than this size, then there's not, then alkanes and ethers are about the same. All right, now let's compare alcohols and amines. So look, in both cases, the alcohol has the higher boiling point, right? It can only have one hydrogen bond, where these primary amines can have two, but that hydrogen bond is much stronger because the OH is more polar. So we go from ethers to amines and then back to alcohols. Melting points are going to follow the same trends as we saw for boiling points. And so we're not going to, you can read about these more in the book, but I'm not going to say anything more about them at this point in time. So the last thing we're going to take is the solubility, right? So whether a molecule will dissolve in water or whether it'll dissolve in a more organic solvent, like something like hexane or ether or something like that. Okay? So the general rule that you've all heard before is that like dissolves like. And what this means is that polar compounds are going to dissolve in polar solvents. And so the most polar solvent that we can really have is water, right? And the most polar, what are the most polar kind of compounds? Okay, so the most polar kind of compounds are ionic compounds. And so we already know that most salts, right, which have cations and anions, can dissolve in water. All right. Nonpolar compounds are going to dissolve in nonpolar solvents. So like I said, an example of a very nonpolar solvent is hexane. So nonpolar compounds are going to be things like, like alkanes, right? All kinds of hydrocarbons, right? But also things like ethers, right? And for a lot of functional groups, it depends upon how many carbons there are per functional group. So let's look at some. All right, so in order for a molecule to be able to dissolve in water, the water needs to be able to solvate that molecule. Okay, so solvation. What this really means is that it needs to be able to be surrounded by water molecules. And if we think about it, what has to happen is that these YZ molecules, right, we looked at these kind of things already, delta plus, delta minus, and they are having dipolar interactions like this, right? And so what has to happen is that water has to be able to break these dipolar interactions and make stronger interactions with the molecule. Okay? So let's look at this. So here we have the Z group with its delta minus. And so notice how water is surrounding it. It's the hydrogen, the delta plus end of water, here and here, which is being aligned toward the delta minus end of this molecule. And the delta plus end of the molecule is being surrounded by the delta minus end, the oxygen, of water molecules. Okay, so in this way, these dipolar interactions here, these hydrogen type of bonds, are giving back more energy, making this a more stable situation than these types of interactions right here. So this, in this case, this molecule would be very soluble. All right? So, like I said, though, it depends upon essentially the ratio of polar molecules to nonpolar molecules. Okay, so if we look at a series of alcohols, all right, so here we start with methanol right here, methanol, ethanol, propanol, butanol. Okay, so the very smallest one, methanol, is very soluble in water. Right, go to ethanol. Ethanol is still very soluble. Right, we have ethanol in drinks; they dissolve in water. Right, and we go to propanol, is still soluble, but when we get to the size of butanol, then it still has some solubility, but it will form two layers. So we call this a limited solubility. Right? It has two layers like oil and water, something like this. This side up here is water soluble. So this would only form one layer. These would be miscible. The one butanol and bigger would be immiscible with water. All right? Even when there's two layers, there can be some limited solubility. So the water layer will be saturated with butanol, and the butanol layer will be saturated with water. Okay? So let's look at ethers next to it. All right? So we have dimethyl ether is small. Methyl ethyl ether, then we have methyl propyl ether, and it turns out when we get to this point, okay, these are water soluble, and these form two layers, limited solubility. All right, diethyl ether, like this, also will form two layers with water. Okay, so that's at the same size as, right, as methyl propyl ether or methoxy, 1-methoxypropane. This one and diethyl ether, these have the same masses and they have the same functional group. All right, so in general, for oxygen, for these types of molecules, if we have greater than around, this is just ballpark, 3 to 4 carbons per oxygen, okay, it will be insoluble, or at least it'll form two layers with water. Okay, so an example of something that could be very big but still be soluble would be something like this. If you have alternating molecules like this, okay, then let's look at 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 10 carbons, and we have 1, 2, 3, 4 oxygen, right? So our ratio is 2.5, so this would be water soluble. Okay, just as a summary, we've come a long ways in this chapter, right? We learned about some functional groups up here, right? Then we learned how to name them down here, right? We've learned about some of their properties down here, like boiling point, melting point, and solubility. We spent a lot of time talking about alkanes, right? We learned how to name straight chain alkanes, which form the basis for all of our IUPAC naming, and we learned how to name branched chain alkanes as well. We then learned about their different conformations, which are formed through rotations around single bonds. We then went on and talked about cycloalkanes, particularly focusing on cyclohexane. And we learned how to name these cycloalkanes, and then we talked about the conformations that are available to cyclohexane as well, and how to draw the chair conformations.